This pre-calculus algebra video will provide an introduction to logarithmic functions, often abbreviated logs. We can use logs to find a number of different applications. One has to do with decibels and sound level. We use logs to find an exponent, and that's often used for decibel levels. Here are some examples. Now, the very first step in understanding a log is to understand what a log is. In its most basic form, here's what a log is. A log is finding the exponent. The purpose of the logarithmic function is to find the exponent. So the log is the exponent. When I take a log, that means I'm finding the exponent. Here's an example to our left here. If we have 5 to what exponent equals 25, then the log base 5 of 25 is the exponent. Well, this one maybe comes really easily to you as 2, but the log base 5 of 25 is 2. The exponent, when the base is 5, and you get a result of 25, the exponent is 2. That's what a log means in its basic form. The very first step to understanding logs is to know this connection between an exponent and a log. So in some ways you could see this as the definition of a log. You can't say, oh, I don't understand that. It's not so much understanding it as it is knowing it, just knowing what the definition is. The definition of a log is that it's the function we use to find the exponent. So the log is the power, or the exponent. We can see that as the orange y. What is the log base b of x? It's this orange y. What is the y? It's the exponent. So if we had an example like b to some exponent equals x, and you're trying to find the exponent, how do you get the exponent? You take a log. The exponent is equivalent to the log base b of that green x, of what it is that we got when we raised the base to the exponent. Well, let's jump in and try some examples. We're just simply going to make a translation using the definition. Log, to start with, you want to be able to read these, and the way I'd read this is log base 6 of 216. So if the base is 6, base is 6, I'm trying to find, oh, you know what, I'm sorry, let me go back and use the same colors that I used before so that it matches up a little bit more nicely for us. The base is 6. So 6 to what exponent? The exponent of y. 6 to what exponent equals 216. 6 to what exponent equals 216. And that's all that we're doing here. Now, I could use a log to find that exponent, but all that this is asking us to do is to write it in its equivalent exponent. I know you might be dying to know what it is, right? So let me give you the answer. You may have already gotten that, but it was 6 cubed. 6 cubed is 216, right? So what is the log base 6 of 216? It's going to be 3, because what does a log do? It finds that exponent. Now in this question, it's asking us just to write it in its equivalent exponential form. So this is all we needed to do. But to help you get a better and better understanding of what it is to find logs, I'm going to give you some of those answers also. So write the equation 7 to the y power equals 200. Write this in its equivalent log form. So it looks like we have a base of 7, and the exponent, what we're trying to find, is the y. So the log is finding the exponent. So I'm going to start with the y equals log And then what is the base? It looks like the base is 7, right? Log base 7. And of what? What are we getting as the result? It's that green 200. So if I raised 7 to some power and got 200, what would that exponent have to be? If you were to use a calculator and try that a few different ways just by trial and error, you might get that the exponent is between 2 and 3, closer to 3, approximately 2.7. So 7 to the 2.7 exponent equals 200. But if we wanted to write this equation, 7 to the y equals 200, as a log, we'd say y, the exponent, equals log base 7 of 200. Let's look at example 3. We can evaluate some logs by simply rewriting these in their exponential form. So it looks like we have a base of 5, and we're trying to find the exponent. So 5 raised to what exponent is 1 over 5? Do you see that one? Do you remember some log properties? I'm sorry, not log properties, but exponent properties. Do you remember this one? A to the negative r equals 1 over a to the r. Or if I have a fraction a over b and I raise it to a negative exponent, if I wanted to make that exponent positive, then what I do is I write it as, I flip it, so I write it as a b over a. B over a. So we flip it. Do you see what I could do to get this 5 into a 1 over 5? I'd have to flip it, right? So you guessed it, it's its reciprocal. So it looks like the log base 5 of 1/5, log base 5 of 5 to the negative 1 is going to equal negative 1. Just by translating that into log form. If I go from log to exponent, I'm saying 4 raised to what exponent equals 16. I can write the 16 as a 4 squared. So that missing exponent is a 2. Log base 4 of 16, just by using the definition of what a log is, I'd get that that exponent is 16. So what exponent do I raise 4 to get a 1? Oh, do you remember that one? Do you remember that exponent property? 4 to what exponent equals 1? Remember that any base raised to the 0 power is going to be 1, right? So that missing exponent, 4 to what exponent? The exponent is 0. When I find the log, I'm finding the exponent. The exponent that I'd raise this base to is a 0. So log base 4 of 1 is 0. Let's look at this graph. We could do a graph by making a t-chart. Have you caught that the exponential function and log function are inverses? So I should see that because they're inverses, when I graph them both on the same line, or I'm sorry, graph them both on the same axis, xy plane, I'm going to get this fold line at y equals x, and I'm going to see that the two graphs are going to reflect or be symmetrical about that line. That what happens on the right side of the line for one function will copy over to the other side of the line for the other function. But just by plotting some points, I could do a chart and work out 1/2 to the negative 3 to the negative 2 to the negative 1 to the 0, 1, 2, 3. And then once I have these ordered pairs, do you see what happens for an inverse? For an inverse, do you remember that the x's and y swap? For inverses, do you remember that you swap the x and y? So if the log is the inverse of the exponential, then we're just going to swap the x and y. So I'd swap negative 3, 8. Now y becomes negative 3 and x is 8, and so on. So if I graphed these points, negative 3, 8, and here's what the graph would look like. If I graph the exponential function with base 1/2, I'd get this black graph. If I reverse across that full line, if I reflect across the y equals x, or in other words, if I swap the x's and y's, I can get its inverse. I could get the graph of log base 1/2 of x. When I reverse the x's and y's, I'm going to reverse from negative 3, 8 to 8, 3, negative 2, 4 to 4, 2, negative 1, 2 to 2, negative 1, 0, 1, and 1, 0. Down here, plot that one. And then 1 negative half goes to negative half. 1, 2, when x is 2, y is 1/4. So when x is 1/4, y is 2. And then 3 1/8 translates to 1/8, 3. And we're going to get this sketch here. Do you see if I fold it on this line? These points, this red, green, blue, is identical over here, red, green, blue, and the purple, green, we can see the reflection. So that's what the graph would look like. Sometimes the best way to graph a log function is to simply start by graphing the exponential function first, and then find its inverses, reverse the x and the y points. Let's talk about the domain of a log function. It's here in the definition. Let me highlight it for you so you can see that. It's got to be that x is greater than 0. What we're taking the log of has to be greater than 0. It cannot equal 0. It's got to be greater than 0. So when we're finding the domain of f of x, when f of x is log of 2 minus x, we're going to let the 2 minus x be greater than 0, and then we're going to solve for x. So I could solve this for x by subtracting 2 from both sides, and I'd have that the opposite of x is greater than negative 2, and then I can divide both sides. I can divide both sides by negative 1, and remember that for an inequality, for a greater than, that would switch it to less than. So when I divide by negative 1, I've got to flip that greater than around. So we're going to get all the x's that are less than 2. In interval notation, x is less than 2. Would go this way. So that's going to be negative infinity up to 2 is the domain of f of x equals log of 2 minus x. For domain, go back to that basic definition of what the log is. Here's a good application problem of applying logs. The percentage of adult height attained by a girl who is x years old. So what is x? X is the age. Can be modeled by f of x equals 62 plus 35 log of x minus 4, where x represents the girl's age and f of x represents the percentage of her adult height. Approximate what percentage of her adult height has a girl attained at age 13. If we're given the function f of x is 62 plus 35 log of x minus 4, what we're going to do is go into this equation and replace x with 13. So what would that look like if I go into this equation or this function and simply replace the x's with 13? I'd get 62 plus 35 log of 13 minus 4, so that's 62 plus 35 log 13 minus 4 is 11, log 11. And I could do this now on my calculator. I could put this on my calculator. I could get an approximation anyhow. 62, I'm using a Texas Instruments 30X. And if I type this in, 62 plus 35, and then I'm going to find the log button. And by the way, when I hit log, that implies log base 10. But I hit log base 10 of 11. I don't have to type in the 10, it's implied. And then the parenthesis opens up. I'll type in 11 and close the parenthesis. And I'm going to get that this is approximately 98.4487. It didn't say where to round it. So if it's saying to give a percent, then I'll go ahead and just round it to the 10th of a percent and say that that's 98.4%. Therefore, she has reached about 98.4% of her adult height. At age 13. Let's look at a couple more examples, applications, how we can use logs. Find the domain. If we want to find the domain of a natural log, remember that this x plus 2, what we're doing the log of, has to be greater than 0. So if I solve this for x, I'll subtract 2 from both sides and get that x is greater than -2. Greater than -2, we'd start at -2 and follow the arrow right. So it looks like the domain would be starting at -2 and going up to infinity. And then one more example, another application. The function f of x equals 5 1/10 of the natural log of x plus 19. This function models the percentage of U.S. adults putting off medical treatment because of expense. The expense is the f of x years after 2000. Use the function to find the percentage of U.S. adults who put off medical treatment in 2019 because of expense. Round to the nearest percent. 2019, if x is the years after 2000, then 2019 is how many years after 2000? Well, I could do 2019 minus 2000, and I'd see that 2019 is 19 years after 2000. So we're going to let x equal 19. When I go into this equation, this function, I'm going to find f of 19 is 5.1 times the natural log of 19 plus 19. So f of 19 is 5.1 times the natural log of 19 plus 19. And I could use my calculator to approximate that. F of 19 is approximately, I'm going to type in 5.1. I don't have to say times natural log. I can just hit ln, natural log, and it knows that that's times. So 5.1 times the natural log of 19. So 5.1 ln, the first parenthesis opened up, so I'll type in 19, close the parenthesis, and then plus 19. And I'm going to get 34.016638. Now if I round this to the 10th of a percent, looks like that's 34.0%, or I could say 34%. Oh, it says round to the nearest percent. So there we go, we did it correctly. Therefore, use this function to find the percentage. Therefore, about 34% of the U.S. adults put off medical treatment in 2019. And there we've got it. Well, I hope that this video has helped you have a better understanding of some logs. Here are some important properties you'll want to know and understand. If you haven't done so yet, I'd say that the next step is to watch the video that walks you through these properties. But here's the properties of common logs and natural logs. Now, a common log is a log base 10. Why is that common? It's common because our number system is based on 10. So we work really easily with tens, right? You could do 10 to the third power easily. 10 times 10 times 10, it's 1 with 3 zeros, and so on. So this is called the common log when the base is 10. And then a log that shows up often in nature is a natural log. In some languages, some Latin-based languages, you know how you would put the adjective first? So in some languages, we might say log natural. We'd put the adjective natural but after the noun. So we're going to put, in English, we put the adjective first. So we describe the log as being natural. But if you can think of it as the same thing as a log natural, log base E is going to be log natural log. And I don't think I finished writing this last one, right? Log base 10 is just log. When we don't write the base, it's implied to be 10. When we have an ln, that means log base E, log natural. Don't type in a 1 if you're using a homework system. Don't type in a 1, you type in an L for log. Not 1 natural, but log natural or natural log. Well, I hope that this video has helped you. Please let me know if you have any other questions about the content of this section, and we could discuss it more in detail.